Here's an idealized global circulation map, and we're looking at the equator as the greatest insolation angle, right? The incoming sunlight is going to have the greatest average sun angle, so it's going to have the greatest amount of heat, and the further I move in latitude towards the poles is going to have less. But there are other factors that influence the sun or the heating of the Earth too. Oceans heat up differently than land. We have different albedos of materials on land also. We could talk about proximity to a body of water. We can talk elevation. But all in all, we're going to be using a term called pressure gradient force, PGF. And that's what's going to be driving winds, both in speed and direction. So as we talk about atmospheric pressure, this is the force exerted by the weight of the air above. The weight of the air at sea level is 14.7 pounds per square inch, or 1 kilogram per square centimeter. This decreases with increasing altitude. So here's a picture. If I'm standing at sea level, I have a pressure of 14.7 pounds per square inch. And the higher I am in altitude, so if I'm standing at the top of Mount Everest here in the picture, I have a lot less pressure on me than I would have if I were standing at sea level. Here, the air pressure on Mount Everest is 29.035. In this case, it's 29,000 feet. It's only 314 millibars. It's much, much less than the average standard sea level of 1,013.2 millibars. And that would be the value of the air pressure at sea level. So as I rise in elevation, I'm decreasing in pressure. So atmospheric pressure. The units of measurement can also be measured in inches of mercury. This is standard sea level pressure of 29.92 inches of mercury. Instruments that we measure air pressure is just a standard barometer. And a mercury barometer is one that is not used as much anymore. Mercury is not the greatest material to have in classes or even professional. There's a lot of different ways that you can have barometers that measure atmospheric pressure, but pressure is constantly changing. So a mercury barometer, though, essentially it's measuring how high the mercury is going to travel in the cylinder, and it's going to be based on how much air pressure is above it. So standard pressure at sea level is 1,013.2 millibars, which is the same as 29.92 inches of mercury. These are just two different ways to state the average sea level air pressure. So I'm going back to this picture here. So at sea level. So this is an example of a mercury barometer. So an aneroid barometer is another type of barometer. This is without liquid. It uses an expanding chamber, and there'll be a picture of that here in just a second, right here. This aneroid barometer here is going to be, it's measuring the pressure, and it's going to be able to tell you what those conditions likely are. So low pressure, stormy, and high pressure are fair and very dry. So the higher the pressure, we get these nice conditions. So a barograph is what is continuously recording the air pressure. Before we talked about when we measure a seismic event, we use a seismometer. Well, a barograph is similar to that. And it looks like this. An aneroid barometer, this would be your barograph. This would be the reading of air pressure. And notice in this example here, air pressure would be decreasing. So one could say that, well, here it was probably nice conditions, and then a low pressure moved in. Therefore, the pressure itself is going to be changing. So today's pressure map, if I were to determine the pressure influence, well, the low pressure moved out of the region, right? In general, if I go back and look at the original picture here, our prevailing winds are called westerlies. That air masses move, or air moves from kind of the southwest to the northeast, or just kind of a westerly flow. And if I use this very thinking to today's map, I know that if I look west, that these conditions out here are going to be influencing us here. So low pressure is moving out, so our barometer reading would be increasing. This is a high pressure system moving in. If you can see these white lines on this picture here, these are called isobars, and we'll talk about these a little bit more as we continue to move into this lecture. But isobars are just showing that all of this pressure along this isobar is one particular pressure. That this one here is a different isobar, so it's a different pressure. And if I'm moving toward a high pressure system, I'm increasing in barometric pressure as I move towards the high, which would be the same as saying I'm decreasing in pressure as I'm moving toward the low. So our conditions today are likely to be rising. Our low pressure system moved through, we're moving toward higher pressure. So conditions. High pressure typically come with or associated with clear skies, nice fair weather, and low pressure are often associated with storms or the potential for precipitation. Wind directions. Winds always blow from high to low. So if I'm talking from high to low, right, it's moving in generally this direction. And that's right, our winds are out of the northwest. And wind speeds. And wind speeds are going to be driven by these isobars. The closer my isobars are together, the greater what's called the pressure gradient force. That the closer these are together, it's going to be windy here because these isobars are fairly close together. So we'll keep moving on. So wind. So what is wind? Well, wind is the horizontal movement of air. These come out of areas of high pressure and they move into areas of low pressure. So air moves from high to low pressure. This is what generates a force. So we're going to be using, so what controls wind? Well, it's called pressure gradient force, or PGF. And these are measured by isobars. These are the lines of equal air pressure. And a pressure gradient is simply the pressure change over some distance. And we can measure that and we can quantify that. The greater the pressure gradient force, the stronger the winds. So if I look at this weather map that shows isobars and wind speeds and directions. So here I have a key. So let's not overlook that we have a key here that are going to be denoted by these little features here of these little squiggly lines or flags. So here's a low pressure system. We learned that low pressure systems, air circulates counterclockwise, where high pressure winds circulate clockwise. And you'll notice that winds are moving into a low pressure system, right? High to low. In a high pressure system, winds are moving out of the high pressure system. So low pressure system. So if I look here, we can find Chicagoland area is roughly at 996 millibars based on this map here. So I can use these weather maps that show isobars. These isobars are the solid dark lines that are showing that have a specific number in millibars. So this is 996, this is 1,000, this is 1,004. So the increments are 4 millibars per line. And then I can just correspond it to a particular flag and find that this wind is at this location in southern Illinois, likely to be at Carbondale or ish. Southern Illinois is moving out of the southwest. That's a pretty strong wind, 55 to 60. That seems a little high, huh? 55 to 60 miles per hour. That's a pretty significant wind. But notice these isobars are close together. The closer they are together, the greater the pressure gradient force, the stronger the winds. So what controls the wind? Well, the Coriolis effect. This is the apparent deflection in the wind direction due to the Earth's rotation. In other words, wind doesn't flow in straight lines. This is the deflection to the right in the northern hemisphere, and it's to the left in the southern hemisphere. So we're going to look at what the Coriolis effect is right now. So here's an animation I found online. It's simply saying if I were imagining a plane traveling in the northern hemisphere, a plane is flying from Anchorage, Alaska to Miami, Florida. It would miss its target due to the Coriolis effect, right, if it were traveling in a straight line. The target location where the plane was headed when it took off has moved with the Earth's rotation. So the plane would end up to the right of its original target. Let's look at it one more time. If I'm going from Alaska, if I want to start and I want to end in Miami, if it were to fly in a straight line, the Earth is moving out. It's a moving platform. So it would be deflected to the right. And in the southern hemisphere, it's the opposite direction. So when I look at it from here, you'll see that it's going to be deflected to the left. So here I have an example of the southern hemisphere, a plane flying from a city in Argentina directly toward Rio de Janeiro. In Brazil, it would miss its target due to the Coriolis effect. The target location where the plane was headed when it took off has moved with the Earth's rotation, so the plane would end up to the left of its original target. In reality, pilots take into account the Coriolis effect, so they do not miss their targets. So this is the southern hemisphere, and notice that everything is deflected left, northern hemisphere to the right. So the Coriolis effect is something we have to take into account, that winds that are moving in straight lines are going to be deflected. And we will pay most of our attention in the northern hemisphere, that they are always deflected to the right. Friction. Friction is only important near the Earth's surface, and this acts to slow the air's movement. So when I look here at the Coriolis effect, if I'm moving from the North Pole towards the equator, and the Earth is rotating, remember, it's a deflection. It's an apparent deflection. It's because if I move from A to B, B is in a different location after I get into air. So I'm going to be deflected to the right. So we'll continue to identify this, but it's simply an object that's moving on a moving platform. So there's 3 truths and 1 misconception here. The objects in the northern hemisphere always are deflected to the right. The faster an object is traveling, the greater the effect of the Coriolis effect. And the Coriolis effect is much more extreme near the poles, and it's almost 0 at the equator. So a misconception that water in a toilet does not follow the Coriolis effect. It's moving much too fast to be draining to be affected. So wind. So now we have to start identifying there's a couple different locations of wind. We can talk about wind in the upper atmosphere, or we can talk about wind at the Earth's surface. Let's look at upper air winds first. These are called geostrophic winds. They generally blow parallel to isobars. The jet stream is a common term that you've probably heard of. This is a river of air. These are very high altitude geostrophic winds. And they also travel at a very, very high velocity, about 120 to 240 kilometers per hour, which is about 90 to 180 miles per hour. So they move pretty quickly. So these geostrophic winds. So if I look here, if the pressure gradient force is starting from here, if this is a high pressure and this would be a low pressure here, notice, in theory, we think that that path of air is going to travel in a straight line. But then we have to enter in the Coriolis effect. The Coriolis effect is deflecting it to the right. And because it's deflecting it to the right, the net wind is going to be a combination. It's actually a resultant vector that this wind, even though the pressure gradient force is from high to low, it's going to be deflected to the right. And the further that wind travels, it's going to be deflected more and more. So my pressure gradient force is labeled in red here. The Coriolis effect is going to be to the right of that direction. And so therefore my net wind is going to be the result of the deflection from the pressure gradient force and the deflection of the Coriolis effect. So it's really a composite of both of those winds. So the wind we feel is both the pressure gradient force and the Coriolis effect acting on that parcel of moving air. So if I compare upper level winds to lower or surface winds, right? So I've got upper level winds, my geostrophic winds, there's no friction. It's not coming into contact with the ground. So check this out. So here's my high to low pressure. Here's my Coriolis effect that's deflecting it to the right. My net wind is going to be a combination or a resultant vector of my PGF and the Coriolis. However, surface. On the surface, winds blowing on the surface are going to have friction coming into play. Friction always acts in the opposite direction of the wind itself. So I still have my pressure gradient force in red. I have my Coriolis deflection to the right, and I have friction slowing it down. So winds on the Earth's surface are typically much lower, well, when I say much lower, lower than winds in the upper atmosphere, just because friction is coming into play. So surface winds are affected by friction. Geostrophic or upper level winds are not. Upper level winds are the resultant vectors of pressure gradient force and Coriolis, where surface winds are PGF, Coriolis, and the result of friction. So here's the couple topics that we can apply here. Cyclones. A cyclone is a center of low pressure. Pressure decreases toward the center of the cyclone itself. Winds associated with that cyclone in the northern hemisphere, they are inward and counterclockwise. In the southern hemisphere, they're in reverse. They are inward still, but they are clockwise. We're going to focus on the northern hemisphere. So if you learn northern hemisphere, then you can apply it to the southern hemisphere. So a cyclone is associated with rising air and often brings clouds and precipitation. An anticyclone is a center of high pressure. Pressure increases toward the center. So an anticyclone, in the northern hemisphere, they are outward due to divergence, and they are clockwise. And we'll come back to that here in a second. So if I look at low pressure, they're counterclockwise and they're flowing inward. High pressure, they're moving clockwise and they're flowing outward. It's simply driven by the pressure gradient force. So here, the last slide here for this lecture, airflow with surface cyclones and anticyclones. Here's my cyclone, here's my anticyclone. In a cyclone, I have air being driven inward due to my pressure gradient force. That air is going to converge at the surface. It's going to rise and diverge. It's called divergence aloft. Where on a high pressure system, it's moving clockwise and the winds are moving outward. Notice, rise in the upper atmosphere, air is converging aloft and subsiding and then being scattered and pushed outwards. There you have it.